Everyone talks about solar flares like they're the danger. A bright flash on the sun's surface, that's what knocks out power grids and fries satellites, right? Not quite. The flash is just the announcement, a click of a breaking twig before the avalanche. The real danger is what follows. Billions of tons of magnetized plasma accelerating through space at millions of kilometers per hour, carrying a twisted magnetic field that can short-circuit everything it touches. It's called a coronal mass ejection, and 2026 is shaping up to be the year they hit hardest. Here's what's actually happening on the sun right now. The sun isn't a ball of fire, it's a ball of plasma threaded with magnetic fields. Those fields don't just sit there, they twist, they coil, they knot themselves into increasingly unstable configurations, storing enormous amounts of energy like springs being wound tighter and tighter. Eventually, something has to give. When magnetic field lines snap and reconnect, they release all that stored energy at once, minutes, sometimes seconds. This single mechanism, magnetic reconnection, explains everything in this video. The flares, the plasma ejections, the danger to Earth, the 11-year solar cycle that puts 2026 directly in the crosshairs. One principle running through it all. To understand why a coronal mass ejection is genuinely dangerous, you need to understand what it actually is, not metaphorically, physically. Start with the sun's visible surface, the photosphere. It's not smooth, it's roiling chaos, plasma churning at 5,000 degrees Celsius. Woven through that plasma are magnetic field lines, invisible threads of force that arc up from the surface and loop back down. Sometimes those loops twist around each other, they tangle, they form structures called prominences, glowing arcs of plasma that can tower hundreds of thousands of kilometers above the surface. Structures larger than planets held aloft by nothing but magnetic tension. The energy stored in a twisted magnetic field is staggering. Think about it this way. If you try to push two bar magnets together with the same poles facing, you feel resistance. That resistance is stored energy. Now scale that up to magnetic fields stretching across millions of kilometers with currents of 1 billion amperes flowing through solar plasma. The energy stored in a single active region on the sun can exceed the total energy consumption of human civilization for 1 million years. Now imagine what happens when those tangled field lines suddenly snap. The stored magnetic energy converts instantly to kinetic energy and heat. Billions of tons of plasma, electrons, protons, heavier ions get flung outward into space, not at the speed of light, but fast, anywhere from 250 to 3,000 kilometers per second. At the high end, that's fast enough to reach Earth in 15 hours. But here's the crucial part. The plasma doesn't just carry mass and velocity, it carries its own magnetic field, frozen into the flow like threads in fabric. When that magnetic field arrives at Earth, it can interact with Earth's magnetic field in ways that cause serious problems. Think of Earth's magnetosphere as a shield, which it is. Under normal conditions, it deflects most charged particles from the solar wind, channeling them toward the poles, where they create auroras. Beautiful, harmless. But a coronal mass ejection isn't normal solar wind. It's a shock wave of magnetized plasma hitting that shield like a hammer blow. And if the CME's magnetic field happens to be oriented southward, pointing opposite to Earth's northern field, something strange happens. The fields can connect, link up, magnetic reconnection again. Suddenly, there's a temporary hole in Earth's magnetic shield, and charged particles pour into the magnetosphere in quantities the system was never designed to handle. That's when things go wrong on the ground. The most famous example happened on September 1, 1859. Richard Carrington, an English amateur astronomer, was doing what he did most mornings, projecting an image of the sun onto a screen and carefully sketching sunspots. At 11:18 a.m., he saw something unprecedented. Two intensely bright patches of white light appeared among the sunspot group, moved across the solar surface, and faded in about 5 minutes. Carrington had just witnessed a solar flare, the largest ever recorded as it turned out. But what he couldn't see was what followed, a massive coronal mass ejection, already racing toward Earth at extreme speed. 17 hours and 40 minutes later, remarkably fast, indicating just how energetic this eruption was. All hell broke loose. Telegraph systems around the world went haywire. Operators in Boston reported receiving severe electric shocks from their equipment. Telegraph machines in several cities caught fire. In some offices, operators discovered they could disconnect their batteries entirely, and the machines kept working. The induced currents from the geomagnetic storm were sufficient to power the circuit. The auroras were extraordinary. In the Rocky Mountains, gold miners woke at 1 a.m. and started making breakfast because the sky was bright enough to read by. Reports poured in from Colombia, Cuba, Hawaii, Japan, places that essentially never see the northern or southern lights. Newspapers described the sky as blood red and on fire. Some people thought cities were burning, others thought the world was ending. Now, 1859 was an age of telegraph wires and gas lamps. The most sophisticated electrical infrastructure consisted of single wires strung between wooden poles. The Carrington Event was spectacular, but civilization survived just fine. Telegraph operators had some bad days. Everyone else got a light show. The question that should keep you up at night is simple. What happens when a Carrington-class event hits modern infrastructure? The answer is ugly. Modern society runs on electricity, not just for convenience, for survival. Water treatment plants need power to purify drinking water. Hospitals need power for life support, refrigeration of medicines, surgical equipment. Gas stations need power to pump fuel. Cell towers need power. Internet data centers need power. The supply chains that move food from farms to supermarkets depend at every link on systems that need power. All that power flows through a grid of transformers, massive custom-built machines that step voltage up for long-distance transmission and back down for local distribution. Some of these transformers weigh over 400 tons. Here's the vulnerability. When a severe geomagnetic storm hits, it induces electric currents in any long conductor on Earth's surface. Power lines are very long conductors. Pipelines are long conductors. Even railroad tracks. The currents induced by a major storm are quasi-DC. They flow slowly, almost steadily, in one direction. Transformers aren't designed for DC. They're designed for alternating current at 50 or 60 Hz. When quasi-DC current flows through a transformer, it saturates the magnetic core. The core overheats, the windings overheat. If the current is strong enough and lasts long enough, the insulation breaks down and the transformer is destroyed permanently. You cannot repair a melted transformer, and you cannot quickly replace one. These machines are custom manufactured, require specialized transportation, and take 18 months to 2 years to build. There aren't spares sitting in warehouses. A major geomagnetic storm could destroy hundreds of high-voltage transformers simultaneously across an entire continent. The 2008 National Academies of Sciences report, the one that got Congress's attention, estimated that a Carrington-class event today could cause $1 to $2 trillion in damage in the first year alone. Full recovery might take 4 to 10 years. 4 to 10 years without reliable electricity across large regions. Think about what that means. Anyway, think this is hypothetical fear-mongering? It already happened, just smaller. March 13, 1989, a coronal mass ejection hit Earth's magnetosphere around 2:44 a.m. Eastern Time. Within 90 seconds, not minutes, seconds, the induced currents overwhelmed Hydro-Quebec's power grid. Protective relays tripped in sequence. 5 massive transformers failed. The entire province of Quebec went dark. 6 million people without power, not for minutes, 9 hours for most, days for some. Hospitals scrambled to backup generators. Heating systems shut down in the middle of a Canadian winter. Traffic lights went dark across Montreal. The cascade of failures nearly spread into the northeastern United States before operators managed to isolate the damage. And here's the thing, the 1989 storm wasn't even particularly strong. On the scale of solar events, it was maybe a third as powerful as the Carrington event. It was a proof of concept, a reminder that the physics is real and a vulnerability is real. Same mechanism. CME impacts Earth, magnetic fields connect, charged particles flood in, currents get induced in long conductors, transformers overheat. The only variable is scale. Speaking of scale, in July 2012, the Sun launched a Carrington-class coronal mass ejection, massive, fast, the strongest in at least 150 years of records, and it missed Earth by about 1 week. The CME tore through the exact orbital path where Earth had been just days before. Had the eruption happened a week earlier, large portions of the developed world might have gone dark. The data came from the Stereo-A spacecraft, which happened to be positioned to catch the whole thing sailing past where Earth would have been. 1 week of orbital timing. That's the margin that separated continued normalcy from potential catastrophe. Nobody on Earth felt anything. Most people never heard about it. So why is everyone suddenly talking about 2026? The Sun operates on an approximately 11-year cycle. At solar minimum, the surface is relatively quiet. Few sunspots, fewer flares, fewer CMEs. At solar maximum, activity peaks. More twisted magnetic fields, more stored energy, more reconnection events, more eruptions. Solar Cycle 25 began in December 2019. Early predictions from NOAA and NASA suggested a mild cycle, fewer sunspots than average, nothing particularly concerning. Those predictions were wrong. By late 2023, sunspot counts were running well above predictions. Flare frequency increased. X-class flares, the most powerful category, started occurring with unusual regularity. The predicted maximum kept getting revised upward and earlier. Current estimates place the peak of Solar Cycle 25 in late 2024, 2025, or 2026. Forecasts remain uncertain, but the cycle is clearly stronger than expected, potentially the most active since the 1990s. Some researchers think even stronger. More activity means more CMEs. More CMEs means more chances for a direct hit with unfavorable magnetic orientation. Every eruption is a roll of the dice. The good news, people are paying attention. Space weather forecasting has improved substantially since 1989. The DSCOVR satellite sits about 1.5 million kilometers from Earth at the L1 Lagrange point between Earth and Sun, providing roughly 15 to 60 minutes of warning before a CME arrives. That's not much, but it's enough to put sensitive satellites into safe mode and alert grid operators. Some utilities have installed blocking devices, resistors that can shunt quasi-DC currents away from transformer windings. Procedures exist for temporarily reducing load or disconnecting vulnerable grid sections during severe space weather warnings. The bad news, the fundamental vulnerability hasn't changed. Those transformers still take years to manufacture. The grid is still designed assuming major geomagnetic storms are rare events you might plan for but not build around, and our dependence on interconnected electronics, GPS, satellite communications, internet infrastructure has only grown since 1989. So here's where this leaves you. The same magnetic reconnection that paints the Arctic sky with green light can induce currents strong enough to melt the transformers that power your city. The 11-year cycle driving 2026's elevated risk is just the Sun doing what it has always done, storing magnetic energy in twisted field lines, releasing it explosively, and occasionally pointing that explosion at us. The Carrington Event wasn't a freak accident, it was a large outcome from a process that happens constantly. Quebec 1989 wasn't bad luck, it was inevitable physics meeting infrastructure that wasn't designed for it. The 2012 near miss wasn't a close call, it was a demonstration that Earth-crossing CMEs of Carrington scale still happen. That's the perspective that matters. Not that 2026 is definitely the year everything ends, it almost certainly isn't, but that human civilization has become exquisitely dependent on technology that's vulnerable to something the Sun does routinely, something that is statistically more likely during solar maximum, something that will eventually hit us directly again. The flare is just the announcement. The coronal mass ejection is the avalanche. The question isn't whether another Carrington event will happen, the question is whether we'll be ready. If you enjoyed this video, please give it a like and consider subscribing. It's free and you can change your mind at any time. See you in the next video. For a limited time only, we're giving out the first 3 chapters of our complete introduction to stargazing, completely free. Check our page info for the link.